Hello. Hello. Okay, so having calculated all the necessary diagrams, we shall now proceed towards the actual process of renormalization. So what we have done so far is to introduce a regularization, and we have chosen dimensional regularization, which gives us a parameter, regularization parameter, which we call epsilon, and epsilon going to 0 limit corresponds to the dimension of space-time being 4. And as a result of this regularization, all the Feynman diagrams are given as a power series expansion, and there are poles in it. So schematically, it is of this form. So there are certain poles, and then there is a term which is at its called zero order, finite piece, and then order epsilon. So in the epsilon going to 0 limit, these terms are going to go to 0. This is the limit and diverge. So this is how the original Feynman diagram was divergent in d equals 4, and what we have done basically is to parameterize that divergence in certain pole terms and a finite piece. And of course, this finite piece is not, there is no sense in which it is an absolute quantity, because it pretty much depends on what kind of regularization we take. This is one way of parameterizing the divergences. There can be other ways, as we discussed earlier. So the next job will be to find counter terms. In this discussion, the main point is to add additional additional Feynman diagrams which will to cancel poles coming from the original diagrams. Now, of course, this is there is also a choice involved, because when one adds up additional Feynman diagrams, then one could choose to cancel only this, but one could choose to add a finite piece that also will cancel the divergence. What we need is to cancel the divergence. That process doesn't fix a finite term. So these additional Feynman diagrams can have a finite ambiguity in them. So as a result, when we add these Feynman diagrams to this diagram, the pole terms cancel, and what remains is this small f, which comes from the original Feynman diagram, and another finite piece which is coming from the additional Feynman diagrams. So that will be the entire finite piece, and of course there is an ambiguity in that. So there are two things. One is that finite ambiguity in these additional Feynman diagrams, and the other issue is counter terms, determining the counter terms in the Lagrangian. So we now, what we will do next is to go into the systematics of figuring out order by order in the coupling lambda. We have lambda phi-fourth theory. So order by order in the coupling lambda, we will develop a systematics of finding these additional Feynman diagrams and the corresponding counter terms in the Lagrangian, and demonstrate how order by order these divergences can be absorbed within these counter terms. Of course, the additional Feynman diagrams having this kind of pole terms, because they have to cancel them in the epsilon going to 0 limit, they will diverge, and therefore the counter terms will also diverge. But then we will, once we construct such Lagrangian, such additional terms to be added to the Lagrangian, we shall discuss the interpretation of these divergences and this finite ambiguity at a later stage. But before that, before going into that discussion, the fact that there can be a systematics of absorbing such divergences inside fine counter terms is not at all an obvious statement. It's a non-trivial statement, and our next job is to demonstrate this procedure and show and convince that where this non-triviality lies, and which is basically the basis of the proof of the counter term renormalizability of quantum field theories. So consider absorption of divergences. So first consider at order lambda, the first order in lambda. Only divergence that occurs at first order in lambda is the 2-point function, because in phi-fourth theory we know that the divergences occur in 2- and 4-point function, and at order lambda there is a 4-point vertex. This is tree level, and that doesn't have any divergence. So only divergence is in 2.1 pi, and that is this diagram. And we have calculated this result, and the result is lambda hat 1 over epsilon plus this one. That this one is a function of okay, so I have collected these results here. This is the relevant result. So this is so this is the 1 over epsilon pole, and F1 is the finite piece. And so let me just remove this order lambda square term and this right is an arrow. So order lambda contribution in this 1 pi 2-point function is given by the stack pole. Now to absorb this divergence, we need an additional Feynman diagram. divergence I. And that's given by, I'm writing across, this is an extra additional vertex that I'm introducing with one that indicates that the vertex is at order lambda, and that vertex must be minus m square lambda hat times 1 over epsilon plus f1 epsilon m hat square. This object, this additional, this capital F is finite at epsilon going to 0 limit, because that is the finite ambiguity I was discussing earlier. So this, with this minus sign, this is going to cancel this. Okay. Of course, here we had order epsilon terms. This is finite. This is order 1 and then order epsilon terms. This implies our calculation of 1 pi at order lambda is given by, now with this addition of new Feynman diagram, and that result is m square lambda hat times f1 m hat square minus f1 0 comma m hat square. Now, if this is going to be my Feynman diagram, then the question is that what is the additional term that we need to add in the Lagrangian? So recall, so we have to have a prescription of translating the 2-point function, translating the new 2-point function, new vertex, 2-point vertex into a term in the Lagrangian. So that's what I'm discussing now. Recall original Euclidean Lagrangian density and that's given by half del mu phi plus half m square phi square lambda by factorial 4 mu to the power epsilon times phi to the power 4. And so we are removing bar. So removed bar, as we have done many times, several times before, removed bar from notation to reduce clutter. Then from this Lagrangian, we calculated the momentum space version of the propagator, which is given by this, and that's the expression of that is p square plus m square to the power minus 1. And that's only the free part. The full interacting analog of the same thing in the full interacting theory is G tilde connected to P, which is given diagrammatically, which is denoted like this. And that's nothing but a GP series, as we have discussed earlier. and so on. And this, if you call this 2.1 pi vertex as omega square, then after summing the GP series, the expression that we got is p square plus h square minus omega square p. So the point to note is that there is a minus sign here. So whatever contribution we have here, you can the additional Feynman diagram. If you have an additional Feynman diagram which is 2-point function, then that's going to repeat. And when we collect all of them, all these terms, then it's going to give a contribution which has the opposite sign of m square that is sitting there already. Now, if you track how m square appears here in the Lagrangian, then it is as if you can interpret as m square being corrected by a negative contribution. So the same quantity must be sitting there with a negative contribution. Therefore, since the additional term that we have here is given by minus m square lambda hat times capital F1, then we must add the same amount to the Lagrangian. Because it has a minus sign, it should change the sign and replace m square by the same quantity with a plus sign, by the same quantity but with a plus sign. So therefore, if we define these additional terms, additive terms, to be L counter term, so therefore introducing this is the counter term Lagrangian corresponding to this new vertex. We have to multiply by an overall factor of half, just like here we have a half, which is basically the symmetry factor for phi square. Now, so what we have here is basically, if you calculate this 1 pi diagram, what we had calculated this 1 pi diagram at order lambda. So of course, there are higher order in lambda terms, the diagram sitting inside. But if we look at the theory at order lambda, then what will happen with this Lagrangian? This Lagrangian with addition of this counter term Lagrangian, then it will produce at the tree level, we have this diagram. But inside this 1 pi diagram, I will have this diagram according to the original Lagrangian. But because of this Lagrangian, this additional piece in the Lagrangian, I will have another diagram. So inside this one pi vertex at order lambda, this is one pi vertex at order lambda, we have these two diagrams, which is finite. And that's going to repeat in all the diagrams, but since these are higher order in lambda, is going to be higher order in lambda, only I have to consider these two pieces. So at order lambda, GC2 has been rendered finite, and at order lambda, our vertex is 4 vertex is only at the level, at the tree level, which is automatically finite in the original theory. So if you now recall that any connected diagram is given by the sum over tree topology over the diagrams constructed out of 2-point function, connected 2-point function, and all these 1 pi vertices for n greater than 2. In all these vertices, you will have only the 4-point vertex at order lambda. So, and that is non-divergent. So no divergence at order lambda in the 1 pi vertices, higher point vertices. And we just made the 2-point vertex, 2-point connected function finite. We just rendered it finite. So that means this is therefore the theory has been rendered finite at order lambda. Okay.